Okay, so this is really a pleasure to be talking to you all, and very thankful to Michael and Subit and Jennifer for getting it all going. I think I have, 10 minutes, so I'll give you a little summary of what I've been doing with various colleagues here. I'm in the physics department, and I'm also connected with the faculty center for, this is the one that's on catalysis science. So let me see. I think I'm having problem already. Yeah. So just I wanted to mention some of the people that I've been working with. This is over the last 14 years that I've been at UCF. And as you can see, there are several colleagues from your college as well. And a lot of the work that that I've done with colleagues over here has been in the area of 2D materials, and mainly looking at the chemical properties, which of course, for a physicist, that may be a little bit out of a zone of comfort, but that is an area where I can have maximum collaboration with others outside my department. And as you will see, this is something, the motivation for a lot of the work that I'm doing is because of this MGI paradigm. This is something that came about a few years ago under Obama administration, where essentially what you theory and experiment and computer modeling go hand in hand. And of course, a very significant part of the MGI paradigm is also data science and artificial intelligence. And I put this here, that even though we are doing some AI in my own group, but this is something that is missing, and something in which we could really benefit from collaboration with some of you. That this paradigm has really, I think it has helped in the discovery of novel materials, which is basically the area that I work in. So part of what I do and my group does is looking at nanomaterials that are these all functional materials, but some of them in which that it is their optical properties that is important, and then others in which it is the magnetic property. We are also trying to understand strongly correlated systems. This is, if you want to think in simple terms, would be the area where most of the quantum materials would be. And in quantum materials, some of the techniques that my group has developed allow us to really understand where is the quantum aspect coming from. It's of course mostly from electron correlations, and that has been a challenge. So that's something that we are trying to address. We are also working in the area of thin film growth. This is where Prague Banerjee and Titel Yorka come in, and we're trying to do some work with them, try to do a modeling of thin film growth processes, for example. This is another area where we could certainly work with people in other disciplines. Then the last two is where my overlap in chemistry is very strong. This is in the area of surface coordination chemistry, which actually then connects to a lot of things right now in terms of practical applications. Single atom catalysis is an area that I'm working with Fudong Liu in your college. And then also then there are other aspects of nanocatalysis that my group has been involved in. What I'll do today is I'll just tell you a little bit about how defects can play a very important role. This will be in two-dimensional materials. You've heard of graphene. I'm sure a lot of you have also heard of about molybdenum disulfide and transition metal dichalcogenides. And so I'll just pick two examples and tell you about the work that I've been doing with my experimental colleagues, in which we've been able to show that actually both of these materials can be made chemically reactive. So why 2D materials? Well, the thing is that, when we say two-dimensional materials, we're usually thinking in terms of layers of them. So, if you have, so graphene is a very good example, but this could be, for example, a layer of graphene on top, and molybdenum disulfide, which I'll mention a little bit in a minute. And you could actually create structures where you could have this heterostructure, and you could have then chemical reactions essentially going on in between those two layers. And similarly, there could be other examples. But what I'm going to show you that we actually, even without encapsulation, we could be really thinking about this 2D material and look at defects in them. And that's where you see these very interesting properties. So one of the advantage of 2D materials is that they are flexible, they are easy to make, they are also stable, but the disadvantage is that they're inert. So you have to do something to activate them. So for example, this one over here has sulfur. This is molybdenum disulfide with molybdenum in the middle, sulfur on top, and sulfur in the bottom. And all bonds are filled, so there's no possibility of reaction. So somehow you need to do something to activate it. And what we do is we basically go by this principle that, now again, I'm thinking in terms of my chemistry hat, which is I'm thinking in terms of catalysis, that most transition metals, platinum, for example, is a catalyst, right? Something like molybdenum disulfide is not a catalyst. But if we created vacancies in molybdenum disulfide, then what I'm showing you here is the electronic structure. So in a metal, what happens, we physicists think in terms of a level which we call the Fermi level, and that is, it has electrons all the way up to its Fermi level. And so electrons are available and they can take part in a chemical reaction. So that's kind of a descriptor of a transition metal, of a catalyst. Here we don't have, so it is not a good catalyst. But if we can make it come, so when we create these vacancies, we can get these are electronic levels, energies in which electrons can be populated in the material. So if we bring them close to the Fermi level, then they can become a good catalyst. Now, what we find in this one example that I'll show you is that if we created the vacancy, that would do it. But if we create with that vacancy laden structure, if we put it on copper, which is a rather cheap material, then that becomes an even better catalyst. And so without going through details here, this is how can you create defects in molybdenum disulfide. Turns out that it actually, when you make it, defects are usually there. So again, defect engineering is a very big area where, again, a lot of collaboration can be done. And we have already established some of the rules by which we think this material these materials can be catalytically active. There are other applications too, other than chemistry, but let me focus on chemistry here. So again, what happens here is that when you do have defects, then you start getting, this is your Fermi level, and you start seeing levels appear inside the defect. It wouldn't have been, I should have had one without that, but you would have seen that there was a 2 EV gap over here, okay? So now what is happening is that these, because of this, you're populating these states near the Fermi level because of creation of vacancy, and of course by also putting copper underneath it, then what we do is that we look at basically the energy diagram. So we look at the thermodynamics of these systems, but we also look at kinetics, right? Because what happens, and as you can see, just by looking at something, it's pretty mind-boggling over here what we have. Arvind just showed some of these molecules in the systems that he's looking at. So here we take a simple system. We've got carbon monoxide and hydrogen. And what this is showing is how much energy is needed, or is there a propensity for these molecules to adsorb on this material, in this case, the molybdenum disulfide. And this now says, once the carbon monoxide has adsorbed, what is the propensity that it will then react with the hydrogen that is also adsorbed and produce another molecule. And so the process goes on. And so what you do, there are infinite number of ways of looking at it. And so one can only do so many. And so what we did here is we looked at the different paths. So here, for example, if these are all the energetics that we calculated and the rates of different processes, and this would have given us formic acid. On the other hand, if this was the best possible path, that would have given us methanol. And similarly over here, we would have obtained methane. And then if you go this route, we would have obtained ethanol. So we've got all these things competing. So how do we know what really happens? And so that's where the next thing comes in, and let me now show you this. This is all the various reactions, 36 times 2, so 72 of them. And then what we do this kinetic Monte Carlo simulation. So this is almost like going to Las Vegas and you're rolling the dice, and you know what the probability of different reactions are. And essentially what we find in here, because we are also trying to make sure that the partial pressures, so this is your syngas, carbon monoxide and hydrogen, that the ratio is what they are using in an industrial catalyst. And what we are predicting here is that under the conditions that we have, we will get ethanol is going to be the most, we have almost 80% selectivity for that. On the other hand, there's very little for methanol. Richard Blair, with whom I've been working for a long time, he has seen some of the products, but there's a better example that I'll give you in the few minutes that I have that will show you that actually we can predict things that can be seen experimentally, okay? So let me just go over, I think I probably have very few little time left. So what I have here is this other material, which is boron nitride. And in that, defects play an even important role, and much more important role, and some really nice things can happen. So this is this nitrogen vacancy here that we're looking at. And again, from the hypothesis that we're using, when you have a vacancy, there you see, this is my Fermi level, and you get electronic states that are near the Fermi level. Without the vacancy, there would have been no states in this, because it's a gap, big gap, it's an insulator, that's what boron nitride is. But when you have a defect, you have that. And here I will basically show you what happens and maybe give you a little bit of a feel for the kind of things we do. So what you're seeing here is that here now have carbon dioxide, it's coming, it will go near the vacancy, and this is the electron cloud that we have near the vacancy, and you can see the carbon dioxide coming and getting entrapped there. Now, entrapping carbon dioxide is non-trivial, and this happens here, and it gets settled over there, and now I have a carbon dioxide over there, but I still have this electron cloud. And what that does is that I bring in then hydrogen, and then hydrogen comes in, and as you see, it is coming in, and it is trying to get absorbed, and lo and behold, it does get absorbed, okay? And I know I'll just go through the last slide here on these without going through much detail here. Let me just go to this potential energy diagram here. And what this shows is that we can actually go through the process like I was talking before, and you can get formaldehyde or you can get methanol. And in fact, what we were very surprised to find that actually methanol is more, we would predict methanol would happen at lower temperatures than formic acid. And this is the result from experimental data from Richard Blair's group, where he indeed sees methanol to be the product. And at higher temperatures, so this is at 20 degrees, and then he also did it at 120. And then when he goes above that, he does start seeing formic acid, but then several other products also come about. So just to end this, where can we collaborate? Well, as some of you know me, you would know that I am always looking for ways to bring centers to UCF, and I have worked with several of you to put together proposals for MRSEC, EFRC, and then NRT and CCI and so on. So far, we have not been successful, but that doesn't mean we won't be in the future. We have many new people who've joined the various departments, and so we are in a very good position. And I think particularly for MRSEC, if we could get more colleagues from engineering and computer science, that would be a big boost for us. The other thing that even in my own research, if we more infusion of AI. So right now I'm doing, machine learning and so on with my own postdocs and collaborators. But if I could get more interaction with people in engineering, then that would be computer science would be very helpful. Quantum science is another initiative that I'm leading at UCF, and we have actually put together a pre-proposal, and we'll see where we go. So that's another area that we could, of course, benefit from collaborating. So thank you very much for your attention, and I'll stop sharing my screen.